Bonjour, bon après-midi et bonsoir à tout le monde. Je m'appelle Aurel Serena et j'espère que vous allez bien. Je fais cette vidéo pour vous supplier que vous vous abonnez à la chaîne YouTube de mon grand frère. Merci pour votre support et on se voit dans la prochaine vidéo.
Hello guys, welcome once more to another video in our YouTube channel. So in this video we are going to be looking at a tutorial question on moments of inertia by integration. This time around we are going to be finding the moments of inertia of an isosceles triangle about an axis which is indicated on your screen via integration. So if you're new to this channel, make sure you like the video, you share the video with your friends, you subscribe to the channel, and also don't forget to comment your areas of difficulties in further mathematics. Alright, so without wasting much of your time, let's get started. Okay, so here we have the question displayed to us already. This question is referenced. The reference of this question is from the MAFA Further Mathematics WhatsApp group, and it was sent by 1K Emmanuel. So credits to him, because without him sending this question and asking for help, I would have not even thought of making a video on this particular concept, that is moment of inertia by integration of an isosceles triangle. I think in the previous videos involving rotational dynamics, I have done for a rod, for a uniform rod, about an axis passing through the center, passing through one of the ends of a disc, of a ring, and all the rest. So in this video we change shapes and we are taking a shape which is an isosceles triangle. So guys, same methodologies are going to be applied, but a little bit more complex. But anyways, like we do it, we try to explain to you so you understand to the fullest. So the question reads: a uniform laminal of mass m is in the form of an isosceles triangle ABC with AB equal to AC equal to 5A and BC equal to 6A. A, show by integration that the moment of inertia of the lamina about the axis which passes through A and is perpendicular to BC is 3 on 2 ma squared. B, show also that the radius of gyration of the lamina about an axis through A and is parallel to BC is 2 root 2A, and deduce the moment of inertia of the lamina about the line BC. The last part: a particle of mass m is attached at the midpoint of BC. The system is free to rotate about a smooth horizontal axis through A and perpendicular to the plane of the triangle. Show that the moment of inertia of the system about the axis is 51 divided by 2 ma squared. Okay, so if you want to register for preparatory classes for 2024, you can get to me directly on WhatsApp. I am going to pre-register you to the best preparatory group for the Anglophone students. Now, the advantage you get by registering under me is that you are going to have free video lessons from the MAFA website when you're preparing for your CONCOUR, be it engineering or medicine. And an additional advantage for those who are registering under MAFA and you're in Yaoundé, from time to time the MAFA organization will pass around your center, your preparatory center, and give out free explanatory classes to the students that registered under MAFA. So and also for those of you guys who are online and maybe not in Yaoundé and you want to attend prep classes, yes, MIA is present in all regions in Cameroon. So if you want to register, just get to me and I'll give you more information. That is pre-registration. Pre-registration is free. It's just basically registering you under the MAFA organization, but registration will be done when you begin the classes properly, physically. Okay, so let's begin with the first part of this question. A uniform lamina of mass m is in the form of an isosceles triangle ABC with AB equal to AC equal to 5A and BC equal to 6A, and we need to show by integration that the moment of inertia of the lamina about the axis which passes through A and is perpendicular to BC is 3 on 2 ma squared. So the first thing to do is that we need to draw the diagram indicating all the important informations given to us. So we have the triangle ABC. Okay, now a triangle is actually a triangle is basically indirectly oriented. That is, it is oriented in the indirect sense, which means that it is oriented in the direct sense, which means that the points are labeled anti-clockwise. So when I begin from A, I need to label the other points in an anti-clockwise direction. That's why you see A, B, C. You see, moving from A to B, that's an anti-clockwise. Okay, so we have the triangle ABC already given to us. Now we need to indicate the axis, but before that, we have the length of AB is 5A and the length of AC is 5A. Now we have the axis. The axis is perpendicular to BC and is passing through A. So clearly it is a vertical axis which is passing through A. And since this is an isosceles triangle, then this axis must pass through the midpoint of BC. Okay, since it is perpendicular to BC and is passing through A. So it's basically the height of this triangle, and the height will divide it into two equal right angle triangles. All right, so the axis, we can call it delta. So since it passes through the midpoint and BC is 6A, it means that the distance from the point B to the axis is 3A, and the distance from the point C to the axis is also 3A, since the length BC is 6A and the axis is passing through the center of the line BC, of the line segment BC. Okay, now to get the moment of inertia of this isosceles triangle by integration, we start by considering increments. Okay, because generally the moments of inertia of a certain mass is the product of the mass and the distance separating the mass and the axis, since we find the moments of inertia of a certain body from a given axis. So I'm going to divide this whole triangle into increments, and then I find the moments of inertia of every increment, then I sum all the moments of inertia of those increments. Remember that those increments span the whole isosceles triangle. So summing the moments of inertia of those increments will give us the moments of inertia of the whole triangle. Okay, but anyways, you are going to go via another method. All right, so we are just going to choose one increment. All right, so if I take one increment, I'm going to give the characteristics of that increment. The mass of the increment will be delta m. This delta here is stands for a very small mass. All right, so the mass is kind of negligible, but anyways, the mass exists. So the mass of the increment is delta m. Okay, and the increment is in the form of a rod. All right, where the length of the increment is basically h, and the width of the increment is delta x. That is a very small width. The horizontal, I'm just using delta x because I'm just saying horizontal axis for x. All right, so since the width is a horizontal distance, then it is a very little change, delta x. Now the distance that is separating the axis delta from the increment is x. All right, so now having the length of the increment as h and the width of the increment as delta x, then we start by letting lambda to be the mass per unit area of the whole triangle as well as of every increment that we choose. All right, if we take a rod, the increment of a rod will also resemble a rod, and the only characteristic will be the length. So the lambda will be the mass per unit length. Okay, so this lambda here is the mass per unit. When you say mass per unit, the quantity you are taking the mass per unit of, when you're taking the mass per unit of a quantity, the quantity should be the highest characteristic that the increment can possess. In this case, the increment can possess an area. All right, so if it is a rod, when we take an increment from the rod, the highest characteristic that increment can possess is the length. All right, because the thickness is kind of negligible. In this case, since this increment can possess the length and the width, it therefore means that it can also possess an area. And since it possesses an area, then the area becomes the highest characteristic. So it therefore means that lambda is the mass per unit area of every increment we take, and as well as of the whole triangle itself. So lambda will be the mass of the triangle divided by the area of the triangle, and it is also equal to the mass of the increment divided by the area of the increment. The mass of the increment is very small, delta m, as well as the area is delta A. Okay, now the first thing we do is that we find the moments of inertia of that increment. The moments of inertia of the increment is the mass of the increment times the square of the distance separating the increment and the axis. That's the definition of moments of inertia of a massive of a certain mass. Okay, so since the increment has mass delta m, then the moments of inertia of this particular increment will also be delta I, very small. Okay, so delta I will be equal to delta m times x squared. We need to square the distance separating the increment and the axis. The distance is x. Now we need to square, we get x squared. Now we need to find the area of the increment and the area of the triangle. Let's begin by finding the area of the triangle. This triangle is divided into two right angle triangles whose areas are the same because they have the same height and they have the same base. Now you realize that since this is a right angle triangle, then the height is going to be 5a squared, the square root of 5a squared minus 3a squared if you use the Pythagorean theorem. Okay, because the hypotenuse is 5a and the adjacent is 3a. Therefore, the opposite, that is the height of the triangle, we can use the Pythagorean theorem and you're going to get 4a if you use it very well. All right, so the area will be half base times height plus half base times height for the two triangles. Okay, because the two triangles are the same, they have the same base and they have the same height. So half base times height will be half times 3a times 4a, then plus half base times height for the next triangle will be the same thing. When we simplify, we just have 12ma squared. Sorry, 12a squared. Sorry, 12a squared, not 12ma squared. So it's supposed to be 12a squared for the area. It therefore means that the area is 12a squared for the whole triangle. Now, what about the area of the increment? The area of the increment is just the length times the width, and the area is delta A. So the length is h and the width is delta x. Now we need to find h. Okay, and how do we find h? We need to introduce a certain angle. We call it theta, the angle at C. Now this angle goes for the triangle, the right angle triangle AC delta, and the right angle triangle, which is, that is, it goes for this little right angle triangle here, okay, and also the big right angle triangle, that is this right angle triangle. This angle is the same for both right angle triangles. So with that said, if we take tan theta for the small triangle, it's going to give us the opposite. The opposite is the height, the length, which is h, and the adjacent is basically this distance. Okay, and the distance is 3a minus x, because the distance from this point here to C is 3a, and this little distance is x. Therefore, the remaining distance is 3a minus x. So the tan theta for the small right angle triangle will be the opposite, which is h, divided by the adjacent, which is 3a minus x. But this tan theta is also the same for the bigger right angle triangle, and the opposite of the bigger right angle triangle is the height, and the height is 4a. Okay, the height is 4a, while the adjacent is 3a, that is the base. So we also need to equate it to 4a divided by 3a. From here we can find the height. We can find the height in terms of a and x. So h divided by 3a minus x will be equal to 4 divided by 3. So the height will be equal to 4/3 times 3a minus x. So that is the height or the length of the increment. Okay, so the area of the increment, we need to replace the h with the length. That's the h with what we have, and then we multiply it with delta x. Okay, that is the area of the increment. So we are done with finding the area of the increment and that of the triangle. Now the next thing to do is that we need to find the moments of inertia of that increment in terms of lambda and dA and delta A. So clearly, the moment of inertia, remember that delta m, if I make delta m the subject of the formula, I can just cross multiply from this expression here. We can get delta m as lambda delta A. Okay, so my delta I will be, in the place of delta m, I replace it with lambda delta A. Then I need to also multiply it with x squared. So I have lambda delta A times x squared. Now what's the next thing to do? The next thing to do is that we need now to find the moments of inertia of all the increments on the rod. And finding the moments of inertia of all the increments of the rod is just basically changing the delta I and the delta A to di and dA. This delta is a very small change, that is a partial change. All right, why if we are taking d, then we are kind of talking of a total change. Okay, so in the place of delta, I just replace it with d. So di, when I'm using d, it means that I'm now considering all the increments on the rod, so I'm taking a total change. So di will give me lambda dA times x squared. But what is dA? dA is basically coming to delta A and replacing, anywhere I see delta, I replace it with z. All right, so in the place of delta x, I just replace delta with z. So lambda remains lambda. Now my dA is 4/3 times 3a minus x. Now we also need to multiply with this x squared. Okay, then now we multiply it with dx. Okay, so those are the various steps. That is what you do when you want to find the moments of inertia. From here now, any math student who is not even offering further maths can integrate. Okay, since I need the moments of inertia, which is I, this is a first order differential equation. The variables are already separated, so we can just integrate both sides. Now we need to integrate I. When we integrate the I, we get I. If I integrate the right hand side, I am integrating with respect to x. Okay, and when I'm integrating with respect to x, I need boundaries. All right, I need boundaries. So x will begin from where to where? So basically x will begin from negative 3a right up till positive 3a. Why is that so? Now when you indicate your axis, the axis becomes the origin. It's kind of the origin. if you want to separate your distances. So if you want to separate your distances, your origin is like your axis is like your origin. So since the whole length is 6a, and we have seen that to the left and to the right of the axis we have 3a and 3a, it therefore means that at the point B we are going to be at negative 3a from the axis, since the axis is actually the origin, and anything to the left will be negative and anything to the right will be positive. All right, so we are going to integrate from negative 3a to 3a. So that is the interval of x, because x is a distance separating any increment we take from the axis, and that distance will basically be inside the interval of the length BC, and the interval of the length BC with respect to the axis is from negative 3a to 3a. Now if the axis was instead at B, maybe the axis was here like that, then this is going to be 0, and then we are going to be integrating from 0 to 6a, because the total length here is going to be 6a. All right, but since the axis is at the center, then definitely we are going to be integrating from minus 3a right up to positive 3a. So this is what we have, but you realize that integrating from minus 3a to 3a is the same as taking 2 times the integral from 0 to 3a, because the axis divides the triangle into 2 equal parts, and the increments will be uniformly distributed. So basically we can multiply, we can just integrate from 0 to 3a, and then we multiply it by 2. That is integrating from 0 to 3a, then we multiply by 2. All right, because when we integrate from minus 3a to 3a, it is the same as integrating from minus 3a to 0 and then integrating from 0 to 3a. But from minus 3a to 0 is the same as from 0 to 3a, so we can just multiply by 2. And when we multiply by 2, we have 4 lambda on 3 times 2 to give us 8 lambda on 3. Now we need to multiply the x squared with the 3a to give us 3ax squared, and we multiply the x squared with negative x to give us negative x cubed. Now this is basic integration. If I integrate x squared, I get x cubed on 3, but since there's a 3a here, the 3's are going to cancel, and basically we are going to be left with ax cubed. When we integrate x cubed, we get x to the power 4 on 4. Then we need to replace the limits from 0 to 3a. We fit the upper limit. We have, when we fit 0, we have 0, so we just concentrate on fitting the upper limit. So we have a times 3a all cubed. 3a all cubed is 27a cubed, but when we multiply with a, we get 27a to the power 4 minus 3a to the power 4 is 81a to the power 4. Then we need to divide by 4. Now from there, we multiply you have 8 lambda on 3. You can in fact send a 1/3 into both terms. So 27 divided by 3 is 9, and 81 divided by the 3 is 27. We simplify, we look for the LCM, and then now we basically have, when we simplify all of this, we have 18 a to the power 4, but lambda is m divided by 12a squared. Remember, lambda is also the mass divided by the area. The mass of the triangle is m and the area is 12a squared. Remember, I said I made a mistake with 12ma squared. It's supposed to be 12a squared. So when you simplify 18, a to the power 4 on a squared is a squared. 18 divided by 12, 6 can go into 18 3 times, and can go into 12 2 times. So we perfectly get the proof as 3 on 2 ma squared. So basically, guys, finding the moment of inertia by integration is the same all through. You just follow these steps and you're going to get your answer. All right, now the second part says, show also that the radius of gyration of the lamina about an axis through A and parallel to BC is 2 root 2A, and then deduce the moment of inertia of the lamina about BC. So here again, we are still going to use integration because the axis has been changed. The axis is no longer perpendicular to BC, but it is now parallel to BC, though still passing through A. So we are going to use integration again because there's no other method I thought of to use here. There is no other methodology we can use. So we are going to still go via integration again. And I think going via integration again the second time, we are perfectly going to understand how to get the moment of inertia by integration. So let's go. First things, we draw the diagram. Okay, we have, let me just indicate everything. Okay, so the axis is passing through A and it is parallel to BC. So this is the axis in question. We can call the axis delta 1. All right, so this is actually the axis that we need to find the moment of inertia about, because the axis is parallel to BC, so it's basically supposed to be horizontal. All right, so we need to get the moment of inertia of the triangle about that axis before we get the radius of gyration because the radius of gyration is expressed in terms of the moment of inertia. Okay, so to get the radius of gyration, we must get the moment of inertia about the given axis before we go ahead getting the radius of gyration. So we are also going to take an increment. This time around, the increment will be taken horizontally because the axis is horizontal, since we need to get the distance separating the increment and the axis, so they are supposed to be in the same direction. If the increment is vertical, then there will be no distance separating the increment from the axis. All right, because it's the axis and the increment will be perpendicular, and when you're perpendicular, there is no distance between you and that axis. But when you are parallel, that is, you guys are in the kind of, then you have a distance between you guys. Okay, so we have an axis and we can give the length of the axis as 2x, that is x and x. Okay, we could just call it x, but I decided to divide it into the left. The distance from the distance to the left is x, and the distance to the right is also x, though you can also call the whole distance x, and you have the left distance as x on 2 and the right distance as x on 2. But I never wanted to be having fractions, that's why I just considered the total length as 2x, okay, where the left distance is x and the right distance is x. Okay, and the mass is also small, delta m. Now the distance separating the increment and the axis is y. I'm now dealing with the vertical distance, so I'm giving anything concerning the vertical distance y and anything concerning horizontal distance x. Okay, so the distance separating the increment and the axis is y. All right, so here is a representation of the length of the axis, which is 2x, and the width is delta y, because it's a very tiny change, and since it is a vertical something, then it should be in respect to y. All right, so it should be in respect to the vertical distance, and the vertical distance is y. Okay, now we said the mass is delta m. Here's the mass is delta m. So what do we need to get? We need to follow the same procedure. We let the mass per unit area of every increment as well as of the whole triangle to be lambda. It therefore means lambda will be the mass per unit area of the whole triangle, which is the same as the mass per unit area of the given increment. Okay, from there now we need to find the moment of inertia of the increment, and it is clear the moment of inertia of the increment is the mass of the increment times the distance times the square of the distance separating the increment and the axis. The distance is y, we need to square the distance to get y squared. Now the next thing we need to do is we need to find the area of the increment and the area of the triangle. We already found the area of the triangle. The area of the triangle was 12a squared, right? So now we need to find the area of the increment. So how do I find the area of the increment? I need to take the length times the width. The length is 2a and the width is delta y. Okay, so we have 2x, sorry, the length is 2x and the width is delta y, so we have 2x delta y, but we need to find the x in terms of y. Okay, so to find x in terms of y, we can now inscribe an angle here. That is, if you put an angle here, okay, if you put an angle there, we call the angle theta. If I take this, theta will be the same angle if we consider this right angle triangle, and the same angle if I consider the bigger right angle triangle. Okay, so if I'm taking the tangents of that angle, okay, if I'm taking the tangents of that angle, the opposite to that tangent, the opposite to the angle will be x, and the adjacent will be y. Okay, what of taking the tangent of the angle for the bigger right angle triangle? The opposite will be 3a and the adjacent will be the height, and the height is 4a. All right, so clearly we can use the tangent of the angle. So tan theta will be x divided by y for the small right angle triangle, and for the bigger right angle triangle is going to be 3a divided by 4a, and 3a divided by 4a is 3 on 4, which means that x on y is equal to 3 on 4. Since we need x in terms of y, then we are going to have x to be equal to 3 divided by 4y. So the area of the increment will be 2 times, remember it is 2x delta y, so it is 2, then the x there is 3 divided by 4y, then we multiply it with delta y. Okay, so when we simplify, we have 3 divided by 2y delta y. Now what's the next thing to do? We need to get a moment of inertia in terms of lambda and delta a. So clearly the same thing, we just need to make delta m the subject. From the first instant here, we make delta m the subject. Okay, considering just lambda and delta m divided by delta a. The delta m will give us lambda delta a, so we replace delta m with lambda delta a. But to get a moment of inertia, we need to multiply delta m with the square of the distance. That's why we have lambda delta a times y squared. Okay, now we need to find the moment of inertia of all the increments, where we need to change delta to d, taking the total derivative. So we are going to have di to be lambda dA y squared. But what is dA? dA is basically gotten by replacing the delta in delta A with d. So I just need to replace this delta A here, this delta y with dy. Now I need to take now 3 divided by 2y, then I multiply it with y squared to have 3 divided by 2y cubed. So that's why we have lambda times 3 divided by 2 y cubed dy. Now we need to get I, so we need to integrate. But since y is a vertical distance, then it's going to be from 0 to 4a. All right, because my axis is kind of at, like I said, the axis is the origin 0, and since the length of the height of the triangle is 4a, then the maximum value of y will be 4a, while the smallest value will be 0. All right, so y will begin from 0 to 4a. So I need to integrate both sides, integrating y from 0 to 4a. If I integrate y cubed, I get y to the power 4 divided by 4. When I simplify here, the divided by 4 we multiply with divided by 2 to have divided by 8. So we have 3 lambda on 8 y to the power 4 divided by 4. When we fit the lower limit, we get 0, so we just concentrate on fitting the upper limit. So we have fitting the upper limit is fitting 4a. When we integrate it to the power 4, we get 256a to the power 4. 256 divided by 8 is 32, and 32 times 3 is 96. So we have 96 lambda a to the power 4. But what is lambda? Lambda is the mass per unit area, also for the triangle. So we have the mass and the area is 12a squared. 96 divided by 12 will give us 8. So the moment of inertia of the triangle about the axis that is passing through A and parallel to BC is 8ma squared. Now, the radius of gyration is what we need to find. We need to prove that it is 2 root 2a. Alright. So, the radius of gyration generally, in terms of moments of inertia, can be gotten as the square root of the moments of inertia divided by the mass of the whole system. The mass of the whole system is just the mass of the triangle, which is m. And the moments of inertia is 8ma squared. So, we need to take 8ma squared and divide by m to have 8a squared. So the radius of gyration is a square root of 8a squared. And if you use surds, we are going to have 2 root 2a. So we have proven that the radius of gyration of the lamina about the axis through A and parallel to the line BC is 2 root 2a. Okay, now the last part of this question, we need to deduce the moments of inertia of the lamina about BC. Okay, about the line BC. Now you realize that the line BC is actually parallel. Look at it. The line BC is parallel to the main axis. But now, if you want to use a parallel axis theorem, then we need to get the moments of inertia of this lamina about an axis that is passing through the center. Okay, kind of horizontal like this. We need to get the moments of inertia of that. So from the parallel axis theorem, the parallel axis theorem states that the moments of inertia about delta 2, okay, delta 2 is actually, in fact, though I call it delta 1, but let's just call it delta 2 this time around. The moment of inertia of the whole system about the axis through A, that is delta 2, is equal to the moment of inertia of the whole system about an axis passing through the center plus the mass of the system times the square of the distance separating the two axes. Okay, since the height of the triangle is 4a and this axis is passing through the center, then the distance separating the two axes here is 2a. 4a divided by 2, right? So doing that, we can get the moment of inertia of the lamina about an axis passing through the center. We just need to take the moment of inertia about the axis through delta 2, which is the 8ma squared we had. Then we subtract 4ma squared, because when we take m times 2a all squared, we get 4ma squared. Doing that, we are also going to have 4ma squared. But we actually need to find the moment of inertia about the axis through BC. So we still need to use a parallel axis theory. Now, the essence of finding the moments of inertia of the whole system about an axis passing through the center is because to find the moments of inertia of the whole system about the axis passing through BC, we need to use a parallel axis theory. And to use a parallel axis theory, we must get the moments of inertia of the whole system about the axis passing through the center. That's why, since we have about the axis passing through delta 2, then we can get about an axis passing through the center. Then we use the parallel axis theorem to find the moments of inertia about an axis passing through BC, which is basically taking the moments of inertia about the axis passing through the center plus the mass of the system times the square of the distance. The distance that is separating this axis and BC is also the same as 2a. So we are going to have a very nice conclusion at the end, which will help us to deduce. And I'm just explaining. We are not yet deducing. Okay, I'm just kind of explaining. Okay, so this will give us 4ma squared plus 4ma squared, because we have seen that if I get this man here, I just need to replace I delta 2 with 8ma squared. When I take 8ma squared minus 4ma squared, I get about the center 4ma squared, which is this. Alright, so this is 4ma squared. Now, when we still do this, we still have 4ma squared. So at the end of the day, when we add, we get 8ma squared. So the moments of inertia, so we can clearly deduce that the moments of inertia of the system about the axis that is passing through the line BC, okay, is basically the same as the moment of inertia of the system about the axis passing through A and parallel to BC clearly, and that answer will give us 8 MA squared. All right, so we are done with the B part of the equation. Okay, the last part of the equation, we now have a particle of mass m attached to the point B, to the point attached to the midpoint of BC. The system is free to rotate about a smooth horizontal axis through A and perpendicular to the plane of the triangle. Show that the moment of inertia of the system is 51 on 2 MA squared. So here we are not using integration, all right? But it was very difficult for me to draw this, so I decided to do it in space, kind of snap the picture. So this is what we have. So we kind of have we need to find the axis in question here. Okay, the axis in question here is actually this axis. All right, this is the axis that we need to find the moment of inertia about. Okay, but this axis here is actually the axis delta 1 that we had previously, and we found the moment of inertia. And this vertical axis here is the axis that, in fact, the axis of question A. So I'm representing this so that we can use what we call the perpendicular axis theorem, because the moment of inertia, the axis in question here is supposed to be a horizontal axis that is perpendicular to the plane of the lamina, all right, and also passing through A. So that's why I said that the horizontal axis is actually this axis here. All right, so if we use the perpendicular axis theorem, because we know that this we actually know that this axis, and also this vertical axis are all perpendicular to each other, so we can use a perpendicular axis theorem. Now this is a particle here, the mass is m, and it is attached to the midpoint of BC. Okay, therefore it means that it is attached to the first vertical axis we had. So from the perpendicular axis theorem, since we have found the moment of inertia about the vertical axis and also the horizontal axis previously, the perpendicular axis theorem says that the moment of inertia of the triangle about the horizontal axis is equal to the moment of inertia of the triangle about the axis delta plus the moment of inertia of the triangle about the axis delta 1. Okay, all right, so doing this, you are going to find the moment of inertia of the triangle about this axis here, this horizontal axis h, that is, I can call it delta h. Okay, and then later we also find the moment of inertia of this particle about that same axis. Then we sum the moments of inertias. So the perpendicular axis theorem is saying this. All right, that's what the perpendicular axis theorem is saying. So this happens from the perpendicular axis theorem. So we can just get it directly by taking 8 MA squared plus 3 on 2 MA squared, because 8 MA squared we had it previously, 3 on 2 MA squared we had it from the beginning. We are going to have 19 on 2 MA squared. Now the moment of inertia of the particle itself, all right, about that axis is basically the mass of the particle times the square of the distance separating the particle and the axis. The axis is actually passing through A, okay, and the particle is the midpoint, is located at the midpoint of BC. So the distance separating the particle and the axis is the height of the triangle, which is 4a. We need to square it. We are going to have 16 MA squared. So the moment of inertia of the whole body, that is of the system, about that horizontal axis is basically given by summing the moments of inertia of the triangle to the moments of inertia of the particle about the same axis. So we are going to have 19 on 2 MA squared plus 16 MA squared. Doing that, we are going to have 51 divided by 2 MA squared, and that gives us the moments of inertia of the whole system about the axis that is passing through A, horizontal and perpendicular to the plane of the lamina. So guys, we have come to the end of this video. If you love the video, make sure you like the video, you share the video with your friends, you subscribe to the channel, and you also comment on your areas of difficulties. Don't forget to pre-register for your preparatory classes, which will start immediately after the GCE. Thank you guys for watching once more, and see you in the next video.